Welcome to Optics. In today's lecture, we're going to be looking at geometric optics. We'll be revising what you learned last year and preparing to extend you next week. Geometric optics is one of several different ways of describing optical phenomena. It is the most simplest, it's the most intuitive. We'll start this lecture by talking about where our geometrical model comes from. Where do the idea of rays come from? We'll then talk about refraction and how you can change the direction of light. You can make those rays change in the angle that they're going. We'll then look at refraction from surfaces that are not flat, they're spherical. And we will see how we can then make spherical surfaces, tailor them in order to focus the light exactly the way we want it to focus. So we're going to look at thin lenses. This is going to be quite important in our course and in our laboratory component. Finally, we'll look at a small example, well, it might actually not be quite as simple as you first expect, of a magnifying glass. Become flat. Geometrical optics has strengths and limitations. We are not going to be considering light as a wave, but we're going to be considering light simply as rays that go in straight lines, as long as they're in a uniform medium. Those rays are normal to the wavefront and they indicate the direction of propagation. Now, for geometric optics to be strictly true, we need to always be considering elements that are much larger than the wavelength of light. And in these conditions, we can neglect wave effects such as diffraction. So the relationship between geometric optics and wave optics, or physical optics, is kind of similar to that between classical mechanics and quantum mechanics. Now, finding analytical solutions to problems in geometric optics is quite rare and very hard, but we're going to be dealing with a lot of approximations. One of the ones that we'll use is when spherical wavefronts are far enough away from their source, the wavefronts increase in radius until they are, at least in a small area, where they are planar. And so in this case, we can consider the wavefronts to be planar and the rays to be traveling parallel. So geometric optics is also called ray optics. You might be most familiar with it as a way of describing how rays of light will travel through a complicated series of lenses. So, for example, in a camera lens, you'll have a whole bunch of pieces of optics, and you can use ray optics, ray tracing, to figure out how the light is going to be going inside that lens. There are other places that use it as well. Acoustics engineering uses ray tracing to find out where the sound goes. Computer graphics, the more detailed and more complicated computer graphics use ray tracing to follow the light from a virtual light source of the object to a virtual camera. Electron microscopes use ray tracing. In this case, we're not talking about light at all, but electrons. And you can even use ray tracing to work out where earthquakes came from. And in doing so, you can find about the structure of the Earth by working out how the rays of the earthquake have been bent or reflected. Geometric optics basically uses two laws. One is that of reflection, and as you know, very familiar with that, it also is used in mechanics and so many other things. The angle of incidence is equal to the angle of reflection. Then we have the law of refraction. And in this case, what happens when a light ray approaches a surface, it's transmitted, but it's transmitted at a different angle. So the θ2 is no longer equal to θ1. Remember, our angles are defined between the surface normal and the ray itself. The reason that it occurs is because the waves suddenly change speed as they enter the second medium. And in changing speed, they end up changing direction. First of all, what is it? How does it happen? Well, we can describe it using Snell's law. I don't know why it was called after Snell, because he didn't actually discover it. In any case, what we have is medium 1, we have the light coming in. It comes in at an angle θ1, and the refractive index on that side we're going to call N1. It turns out that the product of the refractive index and the sine of that angle are equal to the product of the refractive index on side 2 and the angle, the sine of the angle on side 2. But since our refractive indices N1 and N2 are different, it also means that sine θ1 and sine θ2 are different. So why does it occur? The reason it occurs is because the light is changing speed. Okay, so we have in this case the light is traveling at speed v1, and on the other side it's changed speed. It's traveling at a speed v2. And I don't know if you've ever found yourself in a situation where you've got wheels on one side of the car going faster than the other, or if you're pedaling and you've got one arm pedaling, or you're pedaling on one side faster than you are on the other. But in such a situation, you will change your direction. So that is the phenomenon that happens right at the interface, at that point there. That's where the change of direction occurs, and it's because as the light is going through on one side, it starts to go faster, while on the other side, before it's hit the second medium, it's still going slower. So what has speed got to do with refractive index? Well, refractive index is simply a way of talking about the speed. It's just a way of giving it a name or a parameter. And the refractive index is given as a ratio between some kind of reference speed and the speed in the medium. So our reference speed we're typically going to use, for light anyway, our reference speed, we're going to use c. That's the speed of light in vacuum, divided by the speed of light in whichever medium we're interested in. Now, if a wave's travelling along, it's going to have a certain frequency. So that is the rate at which the electromagnetic fields change. Okay, so this is our fundamental thing that occurs. So it might be because something is oscillating up and down an antenna at a certain rate, or an atom is vibrating at a certain rate. So there's some kind of physical phenomenon where there's a vibration going on, and that occurs at a certain frequency. Then waves are emitted, and the wavelength of those waves is going to depend on the rate at which that oscillation was occurring and the speed at which the wave moves away. So as a reminder, we have this equation here where the wavelength of the wave is given by this symbol here is a V. Oops, I'm sorry. Okay, divided by the frequency. Now, why am I doing this thing? I am not trying to trick you. I'm actually trying to prepare you for the fact that sometimes textbooks use the Greek letter nu in order to talk about frequency. So these equations here are exactly the same. You can use V for velocity or C for the velocity of light in vacuum. And you can use F for frequency or you can use nu for frequency. The most confusing thing would be if you wrote V over nu. It would be really hard to figure out, but just be aware, okay? I'll try and use F because I think it's just clearer. So in this problem, which you'll continue working on during the tutorial, you're going to be looking at an electromagnetic wave, in this case a microwave beam. It's going to be hitting a rectangular slab and then exiting the other side. So you're going to work out what happens to the direction of the ray inside and what happens to the direction of the ray when it exits the outside. You'll also work out the frequency of the microwaves when they are inside the dielectric. Now, in the normal situation, when light is traveling from a low refractive index to a high refractive index, then any angle of incidence will result in an angle of transmission. That's slightly different. However, if we reverse the situation, and so now we have light traveling from a high refractive index to a low refractive index, you'll find that above a certain angle of incidence, the light is then going to be transmitted at 90 degrees. And then there's no further solution because you can't find theta when sine theta is equal to a number that's greater than 1. What happens then is a phenomenon called total internal reflection. Actually, the reflectivity then becomes 1, or that is, it's 100% efficient. And obviously that is the key idea about optical fibers, the way that light can travel so very, very far. And even in our NBN, the light can travel very, very far without losing any intensity at all. And it does that by the phenomenon of total internal reflection. And of course, fibers are great. You can even give them a slight bend and they will still continue to make sure that the light stays entirely confined. Now we're looking at a phenomenon called chromatic dispersion. Often you ask someone what's the refractive index of a particular material and they'll give you a single number, but that's not actually true. You actually need to specify the frequency of light, or perhaps the wavelength, if you want to correctly specify the refractive index, because refractive index is dependent on the frequency. Let's have a look at light coming through this prism here. It's refracted at 1 and at 2 interfaces. So we can actually look at the change in angle, the angle of deviation through the prism. Now, the important thing to notice in this situation is that the red light which ends up going in this direction, has a certain angle of deviation, but the blue light has a different angle of deviation. And this is because the blue light sees a higher refractive index than the red light sees. The phenomenon of rainbows are also related to this. We have 1, 2 refraction events, and we also have a reflection event. The reason we see a rainbow is if you imagine your eye out here, the blue light is being bent by a certain angle, so the blue light is traveling like that. So that's the blue light that arrives at your eye, whereas the red light is bent at a slightly lesser angle. So it's actually traveling like that. You can see I've just moved these rays up to here, but I've put their points coincident at the entrance to your eye. And so, as you can imagine, you would see red at the top of the rainbow and you would see blue at the bottom of the rainbow, which is in fact exactly what. Now, the ABI value is a useful value for applied optics because it tells us about the refractive index variation of a type of glass. And another name for the ABI value is the dispersive power. So for visible optics, it's defined by this expression here, where we have the refractive index of somewhere in the middle of the spectrum, in the yellow or orange, and the numerator and in the denominator we take into account the refractive index of the glass to red at one end of the visible spectrum and blue at the other end. Sometimes slightly different wavelengths are used, but they're always defined. So refractive indices and ABI values for many materials are listed in tables for looking up the appropriate glass. What it physically is telling us is about the ratio between the mean angular deviation which in this case is going to be sort of yellow to the refractive index of corresponding to yellow light. That's going to be our mean angular deviation there, and we're taking the ratio between that and the difference in the angular deviation between the red light and the blue light. So that we can call our delta D. So it's that ratio that we're looking at. So as I mentioned, you can look up tables and graphs to find the mean refractive index. So this can be, as I said, either 589 or 587 nanometers, and the ABI value, which tells you about its dispersive power, and you can use that for finding appropriate glass for whatever problem you're working on. Now in imaging optics, we're going to take light rays that come from one point, an object point. We're going to bend them in some way using our imaging system, and we're going to make them converge again at some imaging point. These points, the imaging point and the object point, are related or linked, and another way of saying that is these points are conjugates of each other. Now the simplest object that we can use to bend the light like this that uses refraction is a lens. We can actually also do it using reflection, and that the object that does that is called a mirror. Now if we have a system of lenses, our imaging system, it's going to be separated by its left side and its right side. Let's label them 1 and 2. It's useful if we define the object space as the space with the origin at this position here and extending out to the left. And on the other side, we can have our image space. So to the left of this, of number 1, interface number 1, we can put a real object, and we can project a real image onto a screen if it's on the right of interface number 2. Both of these spaces, the object and the image space, also have virtual spaces. For instance, a virtual image can be formed on the left-hand side by be it a mirror or a magnifying glass, but you can't actually put a screen at that location. And similarly, we can actually put a virtual object on the right-hand side of V1. There we go, there's 1 and 2, just to remind you again, using fancy optics. In the case of the mirror, you can see that we're not actually dealing with a transmission but a reflection imaging system, but the same thing applies. We have object space here and we have image space here, but you can see the rays have not converged to an image in image space. They've actually converged to an image over here in this virtual space. Now we're going to be using a convention for the signs of our distances. It's known as the Cartesian convention. It is older than the one used in the textbook, more traditional, so more people use it. Perhaps it's less useful from the point of view of if you were doing working with a computer modeling, where it's nice to have one consistent x-axis. But the way that we're working is that on one side we have object space and the other we have image space. And so you can see that we have an origin and at the vertex, and it is positive in that direction for objects, and it is positive in that direction for images. So for a real image and a real object, the distances are going to be positive, and the distances to virtual objects and images are negative. So the distance to the image is going to indicate to us whether it is real or virtual. Another thing that we will be able to work out from some of our calculations is whether the image is going to be upright, as it is located here. So the image point is on the same side of the optical axis as the object point, or if it's going to be on the inverted, where it's on the opposite side of the optical axis to the object point. The other thing we'll look at is whether it is diminished or enlarged. So in this middle example, you can see that the distance from the optical axis to the image point is greater than the distance of the optical axis to the object point, whereas in another situation you'll find that the distance from the optical axis to the image point is less than it is for the distance of the object point to the axis, and in this case, so with the refraction that we looked at before was with a slab, or just, you know, even just like one piece of glass or something like that. And the light would come in from one side at some angle, and then it would be refracted. So instead of going that way, it would go off at that direction. And if we put in another beam like that, then it would also head off in the same direction. But the thing that even if you put in like a different ray like that, then it would also come off at a slightly different angle. But clearly, these are not going down to a point, are they? How do you get rays to go to a point? Because we've been talking about, our object point and some mysterious image point, but we didn't actually say how you can make that happen. So now I'm going to show you that a spherical surface can actually do that for you, at least to a good approximation. So we're going to start off with our object here. All right, we'll look at one ray that comes up. Okay, it hits the glass. You drop an angle there, and you can work out that distance there, so you can work out all these other angles, this angle here, and so forth. Okay, so it's tedious, but it's still, sort of fairly straightforward geometry. And you can work out where this ray goes and where it crosses the optical axis again. While I'm here, I'll also introduce this idea here. This one at the moment it's called S, but what I want you to understand, this one is called the center of curvature. So if you were to, fit a sphere all the way around, then that would be the center of the sphere there. And this point here is the vertex. So the vertex is where is on the optical axis, and it's the furthest that the lens is, well, to the left or to the right. It's where the optical axis crosses the lens. Okay, now what happens is actually something really tricky. And if you take another ray that's coming from here, because remember our point object is going to put rays off in all directions, it happens that this is going to go down and, oh my goodness, I am sorry about that. That's a really terrible drawing. I can fix that. That's okay. Let's do that one more time. Oh, well, it's bent. But anyway, you get the point. It just so happens for a spherical surface that ray is going to get bent and go through pretty much the same point again. And in fact, you can look at any other number of rays going in different directions. They will also bend and end up going through that same position. So the spherical surface has done the hard work for us. It's actually taken all the rays that are coming from one point and made them converge onto another point. So there is our object and image conjugate points. So what we're going to do is we're going to say that this distance from the object to the vertex, we're going to call this little o. And we're going to say, in this case, that is of course positive, isn't it? And then we're going to take the distance from the vertex to the position where all the rays converge again, and we're going to call that distance u. Oh, no, we're not. That's going to confuse you. We're going to call it little I. And we're going to use r to describe the radius of curvature. So large angles and large distances from the optical axis actually cause problems. In real life, rays that are going through lenses don't usually make small angles. And what happens is we will see that there are various problems that occur, aberrations and the like. However, what we will be doing is avoiding these problems created by large angles, and we're going to assume that the angle of the rays with respect to the optical axis is going to be very small. So then we can use the approximation that sine theta is roughly tan theta is roughly theta. Of course, theta is measured in radians for this to be true. And we're also going to only look at rays that are a short distance away from the optical axis. So the rays are going to be approximately parallel and to the optical axis, and they're actually running along the axis. This approximation is also known as Gaussian optics. Okay, so when you chunk through that, applying Snell's law and making approximations for small angles and small distances and stuff like that, what you can find out is that this distance O and this distance I from the vertex to the object and the image can be related by this really simple equation. So remember that we've got different refractive indices on either side. We've got N1 on side number 1. So this is going to be side number 1, and on the other side, side number 2, this has got a different refractive index. And we can relate these distances using the refractive indices and the radius of curvature. So you can then use this equation to find out I, the distance from the vertex to the image. What we can do is we can use a parameter such as radius of curvature to characterize a spherical surface, but that doesn't really tell us how well it focuses, because the refractive index also comes into the focusing ability. So what we're going to do is now talk about a new parameter called focal length, which is going to be a much more practical way of characterizing a spherical surface. That's going to tell you basically how well or how strongly can it bend light. So the first one, the primary focal length, sometimes called the object focus, it's got several different names. I prefer primary focal length, it's less ambiguous, is the answer to the question, where do I place my object so that my spherical surface makes all the rays come out parallel? And what parallel rays mean is that the image is infinitely far away. So parallel rays mean that I is equal to infinity. All right, so we use this equation here, a paraxial ray equation, and we substitute in infinity for I. And this is going to be our primary focal length. So our object's at the primary focal length, so we'll put that in for our object. Okay, and then all the other parameters we know. So this term here, if you take anything and divide it by infinity, then it equals 0. So that's great, it disappears. You rearrange the expression and you can find that the primary focal length of that surface is given by the refractive indices and the radius of curvature. So I is infinity and O is F1. Secondary focal length is the answer to the question, if I have parallel rays coming in, where are they focused by my spherical surface? So that gives us F2. So chuck an object out at infinity and the image is going to be formed at a distance F2 from that spherical surface. So rearrange that and you'll get an expression for F2 here. If if you go check the previous slide, you'll find that F1 does not equal F2. And the problem is the refractive indices are different on the different sides. So a spherical surface like this has actually got two focal lengths. We can re-express our expression that gives us the relationship between these conjugate distances O and I, and in terms of the focal lengths, the primary focal length and the secondary focal length. Now, in general, the size of the image is not the same as the size of the object. A really good example is if you look closely at the device that you're watching this on, you would say that device is larger than your eye. However, the image that your lensing system in your eye is forming on your retina has to be obviously smaller, doesn't it? You must have a significant diminishing of the object for it to actually fit on your retina. Okay, so we'll talk about lateral magnification. Now in this case, lateral comes from the idea of, which means sort of going out to the side. So, you know, if you have like a tree like that, you talk about the lateral branches coming out to the side. Anyway, so let's just get rid of the tree. It means it's the magnification that is going perpendicular to the optical axis. Now, it's going to be simply the ratio of the sizes of the image to the object. And using some fairly simple geometry, which I'm not going to go through, not because I don't think you can do it, but because I think that doing it doesn't really help you learn more about optics. But what you can show is that the lateral magnification is given by the ratio between the image to the vertex distance, and of course the object to vertex distance, and the ratios of the refractive indices. There's also a minus sign there. That's important to remember. What is that minus sign here? What mean? Well, when magnification is less than 1, it means that your image is inverted with respect to the object. That should be a 0. When the magnification is positive, so greater than 0, then it's up the same way as the object. So the sign of magnification is very important. Something else to note is that if the magnification, the magnitude of the magnification, absolute value is easier to say, is less than 1, then it means it's diminished. And if the absolute value of the magnification is greater than 1, it's enlarged. These are things I'm sure you've learned before. I'm just reminding you. So in this problem, you are going to look at an LED. I'm sure you've seen this kind of thing before. You can see that the little semiconductor die which emits the light is just that tiny, tiny little chip down there. And so that tiny, tiny little chip is going to be emitting rays in all directions, isn't it? Which is not much use that's going to waste a whole lot of light, isn't it? If all you want is for the light to go in the forwards direction. So You want to make sure that light goes in the forward direction. You're going to put a lens on it. So this is inside a little package, and then it's got, you know, a hemisphere on the end. So you can see that this hemisphere is going to act like it's going to be our spherical refractive surface. We've got a refractive index on that side, N1, and the refractive index on the outside is N2. You know what that value is. We've got the diameter of the module, so this is going to be the diameter of the sphere as well, is 5 millimeters, so you can work out the radius from that. So you've got refractive index, you've got radius of curvature. You can now work out the primary and secondary focal lengths of the lens. A lens is a piece of glass with a refractive index of n, a constant value, bounded by two spherical surfaces. And the line joining the centers of curvature defines the optical axis of the lens. So there's the center of one radius, one sphere, there's the center of the other, and you can see that the line joining them defines the optical axis of the lens. What we'll be doing is, for a thin lens, is assuming that the thickness of the lens on the axis is very, very much smaller than the diameter of the lens. So the lens is a basic building block in paraxial geometrical optics, and we'll be looking at how it works using ray optics. If we have a converging lens, then it's going to cause parallel rays to converge to a real focus. If we have a diverging lens, then parallel rays will diverge away from each other. The diverging lens can't actually produce a real image of a physical object. So what we can do is we can work out where the image is formed from a single lens using those formulae that we looked at before. So first of all, we consider a ray that comes from our object. Okay, and so we know that has a distance O to the vertex here. Then what we can do is we work out what would that first surface there do to the ray. And so it turns out that, despite my my terrible drawing, it makes it look as though the ray came from here. All right, so it's made it bent a little bit, and it looks like this is the only real existing ray in this picture. All this dotty stuff is not real, it's just mathematical extensions of that line. It looks like we're forming an image here. So this distance here is I, our first image distance. What we then do is we apply this exercise a second time. So now we call this our object, and we just consider this ray here, which, as you know, it behaves as though it came from over here. So this is now our O. And we look at what happens at this second surface. And this second surface bends it down here. So this distance here is our new I. So we've done a two-step process. We've done refraction number 1 in red and refraction number 2 in green. To see how light is refracted through a lens, We're first going to look at the single refracting spherical surface on the left-hand side that the light sees first. What happens is it creates a diverging ray of light that's heading in this direction. We trace it back, and it seems as though the light has originated from a virtual image located out here. We then apply the refraction of this ray here by the second surface, and it makes the ray converge to our image point. And you do maths. It's not difficult, is it? Like, there's no fancy functions there that you need a degree to understand. So for a thin lens, we have this well-known formula known as the Gaussian lens equation, also known as the thin lens equation, and you can see that we no longer need to have refractive index in this expression because the refractive index in object space and in image space are the same. We're assuming it to be 1, which is the refractive index of air. The thin lens equation, the lens maker's equations, and so forth have been derived using a certain sign convention, so we need to stick with that same convention when we are using those equations. As we mentioned before, those equations are based on using object space and image space. So if we set our origin to be on the left vertex of the lens for object space, then pointing to the left is going to be the positive direction. If we're talking about something to do with images, then we need to talk about them in their image space. And image space has its origin at the right-hand side of the vertex, and it's positive when it points to the right. When it comes to magnification, we're now talking at an angle, perpendicular in fact, compared to the optical axis. We're going to say that our height is going to be positive if it's above the axis. So the magnification then, if we're going to have an image point that points down, that means this has got a height that has a negative value, and our magnification is going to be the height of the image, a negative number, divided by the height of the object, which is a positive number, so this is going to be negative. Negative then is going to indicate that it is inverted. In this tutorial problem, you'll be looking at an equibiconvex lens. Convex means that it's going to be bulging out. Biconvex, both sides bulge out. Equiconvex means that the radius of curvature of one side is going to be the same magnitude as the radius of curvature of the other side. We've been given a focal length, and we've also been, excuse me for that spelling mistake, we've also got the refractive index of the glass. So the question is, can you find out these two radii of curvature? And can you find out what's the focal length when it's in water? Lens power measures the strength or the power of a lens. Just to be clear, this is not the magnifying power, that's something different. So in general, if you have a positive power, then the light will converge. If you have a negative power, the light will diverge. The units are called diopters. They are in inverse meters. So make sure that you have your focal length in meters before you invert it to calculate the power. Ray diagrams are really useful for finding out where your image is located, useful for estimating in order to check if your calculations are correct and so forth. Now, an object point, obviously there are an infinite number of rays that come from that object point, but there are some particularly useful ones that you can draw. Now, the first one that we'll look at is that rays traveling parallel to the optical axis then pass through the secondary focal point. So in the textbook, those are sometimes called PF rays. When you're looking at lenses with a negative focal length, as we are over in the right-hand side here, make sure that you remember that the secondary focal point is actually closer to the object than the lens. Another ray that you can draw is one that travels through the center of the lens, and that one remains undeviated in its path. It's called the C ray in the textbook sometimes. And you can find out where those rays converge. If it converges on the right-hand side of the lens, then that's going to be a real image, and you might need to use traceback if the rays are diverging in order to find out where they have converged, where they were diverging from. There are different types of simple lenses. They have series of different names. I don't want you to remember that all these names have certain positive powers or negative powers or can do various different things. What I want you more to be aware of is not only that you have lenses with different shapes, but you can work out from their names what their shape is. So if it says bi, it's referring to both sides, both radii of curvature. If it says plano, it means one of the sides is flat, and of course if the surface is flat, it means the radius of curvature is equal to infinity. Now we can also have a meniscus lens, which is another name for a convex concave lens. It means that both R1 and R2 have the same sign. Now these next few slides are there just to help you learn the sign convention that we will be using in this course. It's just to emphasize it. You might want to pause it if you like, just to write down some notes. If you want to, you can fill out this table, or you can wait for a couple of seconds and I will fill it out for you. The magnifying glass is the simplest optical instrument, so it's useful to understand it. So its main purpose is to create magnification of the image on your retina, and it does this by allowing us to bring the object to a position that is closer to you than your near point. So your near point is about 25 centimeters from your eye for normal eyesight. So in this case, you can see with the magnifying glass in place, we are now able to put the object a distance that is less than 25 centimeters away from the eye. The magnifying power is really useful quantity rather than the lateral magnification. So there are two ways that we can describe it, but one of them is much easier to draw because the other one involves trying to draw the image on the back of the eye, on the retina. So it's going to be the ratio between the angle subtended at the eye by the image. So we've got the magnifying glass in place here, and here is our image. And you can see this is the angle subtended, theta prime. And we're going to compare that angle to the angle if the object were located at the near point. So here is the angle subtended here, theta. The ratio of those two gives you the magnifying power. So in this problem, you'll work out through your tutorial. You've got a certain object. It's only 12 millimeters high. It's 60 millimeters to the left of a biconvex lens that has a focal length of 40 mils. I want you to do a decent sketch, something nicer than I've done here. Calculate the position, size, and nature of the image. Then move the object to a different position, only 35 millimeters away instead of 60 millimeters away, and work out what has happened to the new image.